Earlier in the series of counting videos, more towards the beginning of when we started to learn about counting in this playlist, you were introduced to Venn diagrams and how they're used to solve counting problems. But now in this video, what we're going to talk about is how the product and sum rules of counting are related to these counting Venn diagrams. And I think you're going to be a little bit surprised to learn that there is no relation whatsoever. For example, if you're thinking about what are the chances that one event within a Venn diagram and another event within that same Venn diagram happen at the same time, the chances that this event and this event happen, you absolutely do not multiply the total number of outcomes in each of those events. So, okay, why not? How does all of this work? Okay, a Venn diagram in regards to a counting problem, any Venn diagram, okay, you start with a system like this. The system, this entire system is a single event. It's the outcomes of a single event. What do I mean by a single event? So we could be, our counting problem could be that we're counting the number of ways we can arrange the letters in the word Tallahassee or something. Okay, well, this system here, the outcomes in this system would be all of the ways we can arrange we can rearrange the letters in the word Tallahassee. That would be the event. You would be looking at this entire counting problem as a single event. And so the system of this single event is here. But like even any one of these slots you can view as an event. So if we look at this third letter here, this is its own event. Okay, well, since this is its own kind of distinct event, well, this has its own separate system diagram. This event doesn't have outcomes within this system diagram. This is all the ways you can arrange the letters in the word Tallahassee. So one event within this diagram would be, so TLLASESEH, etc. That would be one outcome if the system was this entire event. But for this third letter slot here, all of the outcomes in the system would be all of the letters in the alphabet. Now you might say, okay, so that means that each of these events have the same system. Well, the elements in all of these, well, actually not really, because these events are down the chain. So the group is going to dynamically change. So even with these events here, the groups that you're picking from are going to be different because you've already picked letters ahead of time. But even if you were picking from a group with replacement, so then in that case, the groups you're picking from each of these events are the same. These would still be different events with their own system diagram because the contexts are different. This is the third letter here. You might be able to put this third letter somewhere, rearrange it and put it somewhere else, but you're still giving out a letter here, a letter here, a letter here, a letter here. These are all still distinct events with their own separate system diagram. Okay, and again, but in this case, when it comes to the word Tallahassee, even these events have different outcomes because once you pick a T here and an A here, well, the system diagram for this slot then is going to be, whatever so Tallahassee has 13 letters, so there's going to be 11 letters remaining because you're missing two that were picked that were already picked. That would be the system diagram for this event. Okay, so that's the first thing you want to get very clear, that any system diagram is based on a single distinct event. A single distinct event. If these were, let's say this system represented all, a 5-card poker hand. Okay, well the system would be all, if this is the entire event, Well, the system would contain all possible 5-card poker hands. Okay, and so with that, then, what are these when we draw these subsets, sub events within the system? What are these? Okay, well, yes, these are events. These are events. So this might be all of the possible straights. This is all of the possible full houses. This is all of the possible flushes. So these are events. I mean, you can take you can think about it. Here's a certain type of straight. That's a poker hand, right? 5-card poker hand. So yes, these are events. But these events are different than regular events. These events are not distinct events. They're these sub-events of this distinct event out here. What that means is that there's no product rule that you can apply between event A and event B here, or like some rule you can apply between event B and event C here. What do I mean by that? Okay, think about what you're saying. If you said that you're going to apply let's say, okay, you might be thinking, well, it's because they're overlapping, right? That's why you can't apply the product rule. No, that's not what I'm saying at all. So let's make 2 disjoint events here. So this would be all of the possible straights, and this would be all of the possible full houses. So you can't have to have a straight, you can't have any pairs. And a full house has like a 3 of a kind and a pair. So there's no overlap here. And so let's say we calculated there was M possible straights based on a 52-card deck dealing a 5-card hand, and N possible full houses. Okay, there is once again, there's no product rule you can apply between these 2 events because these are not distinct events. Think about what you would be saying. If you asked the question, what is the total number of ways I can get a straight and get a full house? Oh, okay, it's M times N ways. Absolutely not. Pause the video and think about what the answer to that question is. Okay, the answer to that question is 0. I cannot, based on this distinct event that we're analyzing with this system, I can't get a full house and a straight at the same time. No. The product rule, if we were thinking about the product rule between based on getting a straight and a full house at the same time, that would be like if there was a poker table with 8 players at the poker table. And this system here, this card hand was Tim's hand that he was dealt. And then there was on a separate page, we were doing another counting problem based on Craig's, his card hands. And then so there was 2 distinct events there, okay? And then we were asking, what's the total number of ways that Tim and Craig could get a straight and a full house? Then you multiply those because you have, okay, Tim could have a straight with a 2, 3, 4, 5, 6, and with a certain types of cards, and then Craig could have a full house with certain types of cards, and you'd cycle through all of those. That's the product rule of counting. There is no product rule here. Again, these events are not distinct. You can't have these 2 hands at the same time. And then if there's overlap, okay, then in that case, the parallel to the product rule with these indistinct events, so let's say A, B, C, you have a straight, a flush, a flush could be a straight, and then what else? The hand has at least 1 face card, let's say. The parallel to the product rule for these indistinct events is these intersecting regions. What's the total number of ways I could get a straight, a flush, and the hand has at least 1 face card? Okay, you're going to get the total number in this region. And that's the answer. You see, and you can, how do you get this? You use this whole formula. The union formula, that has, with the union formula, you can solve for anything. You can solve for any union you're looking for between just 2 of the sets or whatever. You can solve for any intersection you're looking for. The union formula has everything you need. It has all the different possible intersections and all the different possible unions and all the different possible what's just in each set. Okay, and it's the same idea when it comes to the sum rule, except in that case, the sum rule does seem kind of similar to like the sum rule for two distinct events and the sum rule between non-distinct events do seem kind of similar. Whereas with the product rule, it's obvious they're completely different. Okay, but just remember it is different. It still is different though. The sum rule between indistinct events, you're saying what's the total number of ways I could get a. So okay, if we had the case of the disjoint sets, it was you had a straight and a full house. What's the total number of ways I could get a straight or a full house? So if there was M straights and N full houses, well, then I just add those up, right? Now it looks similar to the regular sum rule. Because since it's an or, they're not happening at the same time. So, yeah, I mean, I can't have things I could do. There is a way I could get a straight or a full house. All right, now with the overlapping sets, then the or is more parallel to unions. With when it comes to and criteria, you're going to be looking for intersections. When it comes to or criteria, you're going to be looking for either the main union or some sub-union, like maybe just A union B or B union C or C union A, or maybe you're just looking for just everything in set B or everything in set C. Okay, but remember though, when it comes to the pure product rule between distinct events, or the pure sum rule, there is no overlap. There is absolutely no overlap when you're using the product rule of counting or the sum rule of counting. Based on the way it's defined and talked about, you're thinking about distinct events. You're not applying the product rule to the exact same event. What's the total number of ways I can throw a curveball and a slider at the same time? What? No, it's distinct events. There is no overlap. If you have M outcomes in one event and N outcomes in the other event, and you want to calculate the total number of ways they can happen at the same time, there is no overlap here. Just multiply them. And same thing with the sum rule. There's no overlap if the events are distinct.